Yes, it's a little bit different to the previous formats, I think, in the sense that both Philippos and myself are going to present something based around the same tool. But yeah, okay, so just a little bit of background. I'm definitely not traditionally from the model-driven engineering community, and neither is Philippos. We both come from a formal methods background. And what we're going to present today is sort of an overview of how we've used model-driven engineering in the setting of formal methods within the railway domain. So, and sort of some insights into where I think it's really useful for formal methods and also where we think it's useful for model-driven engineering, both ways around. So today's topics, then I want to sort of give an overview of formal methods, just very briefly, and what the practice is in the railway industry and what the challenges are for formal methods. Then I want to talk about barriers to uptake, because there's been a whole body of work in this area for 25 years academically, and still these sort of academic advancements are not present in industrial practice. And then the main focus is going to be OnTrack, which is a model-driven engineering tool set that we hope overcomes some of the barriers to uptake. And I'll talk about those barriers as we go through the talk and how we overcome them. So very briefly, and I hope it's not too brief, but it's essentially, if you consider the railway domain as an area, there's certain design and also implementation challenges they have where they would like to apply rigorous analysis around the systems they're designing. So for example, if you take signaling, railway signaling, you probably want very rigorous analysis of the computer systems that are controlling signals out on the railway to ensure things like trains can't crash or they don't change the wrong color of signal, this kind of thing. So there's two levels. There's the design level, which I'm going to talk about today, and there's also the implementation level. But at the design level, railway engineers draw things that look like this track plan at the top here. And it contains things like signals or tracks. So these tracks, AA, AB, etc., are areas of the railway where you can detect the presence of a train. So, and there's other things like points. So this is a split in the railway where a train can change tracks, essentially. That's about it for what I'm going to talk about today, at least. There's a lot more things that can appear. But the idea is this signal S1, if it's showing green, means a train can travel along AA until it gets to signal S3, which might be showing green, red, etc. And then if it's green, it can continue through the plan. Now, the main problem here is these signals and how trains are routed through this kind of system. So this is a very, very simple example. But how trains are routed through the system are controlled by some sort of logic that's written down in tables. So here, for example, there's something called a route, which happens to start at signal 3. And this route has certain conditions on it. So it says this point must be set a particular way. So here it must be set straight across. And tracks AB, AC, AD, etc. should be clear of trains, i.e. if you set this to green, the train coming into this area shouldn't collide with another train. And this is the verification challenge that I'm going to put forward today, at least, is do these rules ensure that trains can travel safely through this track plan? So does this set of control table rules guarantee safety for this design? So for example, so this signal is controlled along route 3A, a train traveling to signal 5. And for example, that requires that track AD doesn't have a train on it. You can see that here. Track AD must be clear. If a designer was to accidentally miss that track out from the design, then of course, if a train is sitting on AD, there won't be a check implemented later on. And if another train was to travel along whilst a train is sitting on AD, the signal would turn green and those trains would collide on track AD. That's a very, very simplified version of what happens. And there's a lot of other things that go on that need to be checked. But this is basically the essence of the verification problem. Can we guarantee that trains don't collide in this manner? Okay. Bit of background, this is work that's been ongoing with Siemens Rail. It's taken a very long time. So we've been working for around 15 years with Siemens on various projects that explore these aspects. And like I said, today we're going to talk about the design level. So but there's also a whole body of work at the implementation level and lots of safety arguments, etc., at that level. Okay. So I've been speaking about formal methods, and all I want to mention today is that we're interested in developing formal models which are mathematically well-defined objects that represent this railway design, so that we can reason about those objects in a mathematical way. And you can write these down in various formal models. I've chosen a couple here, but essentially these range from readable or almost readable through to almost unreadable, through to very, very unreadable. And that's one of sort of the challenges in uptake of formal methods. You need to be almost an expert in formal methods to use them. And if you are working in the railway industry, as a railway signaling designer, you've probably got a traditional engineering background where you wouldn't necessarily study formal methods in this setting. And even to formal methods experts, you can show someone a different formal method and they won't necessarily understand what's happening in that formal method. So the aim of our work is to sort of guarantee three things. It is to address something called faithful modeling, which is how do we know that in our formal model we've captured correctly the elements of the railway domain? So how do I know I've got a signal and I've classified the behavior of a signal correctly in my formal model? The second thing we try to address is scalability, which often a lot of formal methods fail when you put a real world large system in front of them. They just can't scale up to that kind of level. And we'll see how we address that with model-driven engineering in a second. And then the last one is accessibility, which is, like I said, if you consider these, it's not very readable and also not very nice to read. So how can we make these objects more accessible? And I should mention there's other work in this area where people have shown that you can use domain-specific languages to encapsulate formal methods, but probably not to the extent that we have in OnTrack, at least for the railway domain. So what the demonstration is going to be about today is this OnTrack tool. It's very much prototypical, but it's based around a domain-specific language for railways, and essentially allows you to graphically draw railway plans and then generate specification text from them or formal models from them. And then that formal model can be automatically passed into a verification tool that hopefully says, yep, this system is safe. Okay, so that's the setup. And I've only got 2 more slides and then I'll jump into the demo. But essentially, we want to support a lot of workflows here as well. So we want a railway engineer, for example, to take an existing model that they might have defined and import that model into OnTrack. Then once they've imported the model, they might be able to choose between various different formal models to generate. For example, one that uses model checking versus one that uses theorem proving, and prove that safety is upheld in both those formal models. And that just increases confidence in some sense that safety is actually a property of this model. Okay, so this is the supported workflows and what we have. And what I want to do is highlight a couple of things. So we answer the accessibility question with a graphical editor. Okay, so that you are allowing railway engineers to design systems in a format that they are used to. We answer the scalability question via abstractions. So it's a normal scientific idea that if you're considering a system, you might want to abstract certain details. And the same thing happens in formal methods. You abstract in certain ways models in order to consider only essential parts of the model, for example, for coming up with a proof that something is safe. Okay. And then the last thing is we address the faithful modeling because, well, it's a little bit tricky, but essentially here, because we have this DSL, you can check that this DSL captures fairly easily all the elements that you would like for a railway model. And also you can check the translations down to formal models at the bottom. Okay, enough about formal methods and how we address the sort of issues there. But what I want to say is the interplay with model-driven engineering in where does model engineering play a role here? Well, the DSL itself, of course, is something from model-driven engineering, and it's represented as an EMF meta model at this point. The editor we're using is then a GMF-based editor. And I know GMF is becoming slightly dated, but this work is a couple of years old. So we've got a GMF-based editor, and then there's a lot of epsilon kind of parts to this editor. So we use the Epson Wizard language for wizards at the editor level. This allows you to do things like draw multiple tracks in one go, just for ease of use. And then we've got various model transformations going on at the bottom that say, okay, from a domain-specific language or an instance of my railway DSL, I can translate that into a formal model. And this might be via an model-to-model transformation, because the formal model you're translating into might have a meta model, which is great, or it might be straight to the specification text, where you use a model-to-text transformation. And then the last one, and the most interesting one from the formal methods community, is this model-to-model transformation with ETL, which is the idea that on the level of the domain-specific language, the meta model, you can encode abstractions back to that DSL. So this is where you can really implement abstractions for formal methods in a nice way. And you can implement the abstraction once and apply it to multiple formal methods at the bottom of the picture. So you implement it at this level as an abstraction and can benefit by generating different formal models from that abstracted version. Okay. So let's have a look at the tool itself. So this is on track. The scheme plan, or the track plan I'm showing you, is fairly small in size, but essentially you can see the editor and the kinds of things on the right-hand side that can be drawn in the editor. So you can drag and drop things like a signal or a point. You can form routes, etc. And then what you can see at the bottom is you can encode the logical control aspects for this plan. So for example, I happen to choose one. So for example, here you can encode information for this signal that shows which tracks need to be clear and which points need to be facing which way, etc., for this route to be set logically. And yeah, when you highlight, it highlights the tracks and things. So that's the editor side, where railway engineers can come and draw the plans in a native sort of language. What I'm going to do is I'm going to switch to a simpler model to explain the rest of the talk, because this one's a bit tricky to explain things. But what we have here is a much simpler model. I think it's very similar to the one that was on the slides, in fact. And what we can do is we can do things like, okay, here's the model, here's the logic that's been encoded for this design. What we can now do is we can form abstractions in the way that I said. So we can say, compute a covering abstraction. I'm not going to jump into the details of what a covering abstraction does, but essentially it addresses the scalability issue that I was talking about. So if you try to verify this model as a whole, so you want to prove for the whole track plan that trains can't crash, that can quickly get out of scope to the point of this would take a few minutes, and something like the original plan I showed you would take hours, if not days, to verify. And they are by no means big plans at that point. So what covering does is it allows you to say, and this is something that's worked out in the formal methods community, but it allows you to say, you can go away and verify each of these individual parts of the railway that I'm highlighting. And if you verify each of these individual parts, then you have safety of the overall system. And what's nice is, from the design that we originally had in the control table that we originally had, computing this covering, which is just a click of a button in the editor, is essentially a model-to-model transformation that is encoding the formal abstraction. So once you've abstracted your model, you can say, okay, generate this model in a given language, a given formal methods language. So here I'm going to use a language called CSP. And okay, we can, for example, we can prove or try to prove that this area of the track plan is safe. So we can generate our model. That's not doing much other than going away and generating, for example, okay, I need to refresh. Okay, I've done lots of practicing today, but essentially it's generated this formal model for this track plan, and these are the aspects of the formal model. I don't know if there's any that are interesting to see. Probably not. Maybe this one. Okay, so here you can see this is the models that I was showing you earlier on being generated in the back end. But as an engineer, you don't need to look at these really. They're just artifacts that are developed at this point. So what you can do is you can generate this, and you can for example, I'll generate this one, and then I can run the model checker. And you can see, okay, very quickly, because this is a very small aspect of the system, we can say that this proof that this is safe according to these rules that have been encoded succeeds. So we have here the result of passed. Now, I said earlier on in the talk that one thing that needs to be encoded is that for routes. So if we look at this route, it says for this signal, it controls this area of track. So trains can enter this area of track if the signal is green. If I was to example remove now that AD doesn't need to be occupied by a train, so that's what one of the conditions is. AD needs to be clear. If I go and remove that track from the design, there's a very simple design error, and regenerate essentially, okay, save the model, regenerate everything that was previously generated. If I now generate the same check and run the model check-in, you will see that this now fails because essentially AD is missing from the track, so trains can collide on AD. So it gives, what we hope at least is it gives a setting that is very native to someone who's designing these systems to use formal methods. And it's sort of all powered by those model-driven transformations that I was speaking about. Of course, I'm going to stop talking in a second, but of course here there's a failure, and what I haven't discussed yet, but Philippos will discuss shortly, is seeing that there's a failure here and this proof has failed now requires essentially someone to go and look at the formal models and try to figure out what was happening in those formal models, right? So it's very difficult to get information back from a formal model, which is one of the challenges we hope to solve still, or it's partially solved. But yeah, so I'm going to stop here at this part of the demo at least, and ask if there's any questions before we move on to sort of Philippos' part of the talk.